Let's look at proposition 9 of Euclid's Elements book 3. We are given a circle and we are told that there is a point in the circle such that there are three equal line segments falling onto the circle from this point D. So let's mark these points where it is falling on the circle A, B and C. So the proposition says that if these three are equal and they are falling on this circle, then D is the center of the circle. Now let's prove this, that D is actually the center. So let's join AB, let's join BC. And now what we are going to do is bisect AB. We know how to bisect. So we have got the midpoint of AB. So let's hide all these elements that we are not interested in. Similarly, we are going to bisect BC. Again, repeat the same procedure. So we have got the point of intersection of these two. And we have got the midpoint. So again, let's hide this. So we have got E as the midpoint of AB and F as the midpoint of BC. Now we are going to join DE and extend it to the circle. So let's do this first. And let's mark the point of intersection with the circle H and L. And let's join this with a line segment so that I can hide the line. Similarly, we are going to join E and D. Again, points of intersection with the circle. And we create the line segment so that we can hide the. So here now, look at this triangle ABD. We know E is the midpoint, which means AE is equal to BE. DE is common to both the triangles. And BD is equal to AD, radii of the same circle. So using side proposition, we can say that these two triangles are congruent to each other. Since they are congruent to each other, that means angle AED is equal to BED. Remember, we have a line standing on another line making equal angles. Yes. So straight line angle is 180 degree. If these two are equal, that means they both are right angles. And we know through some other proposition that a line which is perpendicular to a point on a chord, if it is perpendicular, it is going to pass through the center. Now let's look at this triangle BDC. Here again, BF equal to FC, FD is common to both triangles, and BD is equal to DC, radii of the same circle. That means these two are congruent. That means all the corresponding angles are equal, which means angle BFD is equal to CF. A line standing on another line making equal angles would be right angles. So that means these two are right angles. Again, we know that a line cutting a chord at right angles passes through the center. So we know that this line HL contains the center. Similarly, line segment KG contains the center. Since both of them are supposed to contain the center, the only point at which it is possible is where they intersect each other. So that means D is the center. Now this is actually, while I was constructing it using GeoGebra, I made it as a random point and positioned it approximately in the center. Let me bring in the actual center. Yes. Now, unless I keep it on the center, these three line segments AD, BD and DC, they will not be equal. Even if I move them a little bit here or there, they will become unequal. But that is the condition for this proposition, that they should be equal line segments. These steps are required to actually rigorously prove them. But otherwise, visually itself, you know that if you move it a little bit here or there also, then the line segments would not be equal. It is only at the center that they will be equal. Whether it is this, A or B or C. That is proposition 9 of book 3 of Elements. Let me remind you, there is a link to a PDF book which describes all these propositions in detail. If you use that link, it will take you to the YouTube video for that book. In the description of that video, there is a link to the actual book. That is just to make sure that I need to update only in a single place the link to the book in case the link breaks. You are free to download, refer to it, share it, and in case you find any mistakes, please do write it in the comment. I will rectify, and the updated one will anyhow be available to you from that page itself. That's it for now.